Okay, partial pressure. What's the big deal here? Well, what's kind of interesting is we can use that ideal gas law equation to calculate the pressure due to each individual gas. And it's a very theoretical idea because it's impossible to do in the real world because you just have, these gas gauges and pressure gauges can't tell the difference from one gas to the other. But it's a pretty interesting theoretical idea, and we can use it to like make predictions with chemical reactions, and it's pretty powerful, but we'll get into that. So, but just how is pressure created in the first place? Here's a little animation that I think might help Bowdy. See the little piston moving up and down, right here? So there's something pushing on it, Bowdy, keeping it up. The little guys flying around are supposed to be what molecules? Gas molecules. So in your own words, how would you say pressure is created?
Well, the gas molecules are pushing against the top, which is pushing against the gas.
Yeah. The gas molecules are slamming into the top, pushing it up, right? So if you didn't have a container, it'd be pretty hard to identify pressure. There's nothing to hit against. So you have to have a container, right? And the harder they hit, right, the more pressure they should exert. The more often they hit, the higher the pressure they should exert, right? So that's the concept that you need to have in your head. That'll be pretty helpful. Okay. So here's a container, and it's got, now you can't, this is static, so you can't see these molecules flying around, but it's got hydrogen flying around in one container, and then helium flying around in the other container. And what they're saying is let's combine these 0.6 moles of hydrogen and the 1.5 moles of helium, right? Let's put them all in the same container. But they're trying to say the pressure due to the hydrogen container is 2.9 atmospheres. The pressure due to the helium container is 7.2 atmospheres. I guess if you put more helium in there, the pressure would go up, right? Because there'd be more gas. But if you could actually combine those, so you end up having, I guess, 2.1 moles total, what would be the total pressure? What would you guess, Alyssa? You have 7.2 atmospheres in this one, 2.9 in this one. Pretty much just add them up, yeah. So if you add them up, yeah, there's just some of the moles, right? Some of the pressures. So what they're trying to say is that this idea of partial pressures, that even though the total pressure is 10.1 atmospheres, the pressure due to the helium molecules is 7.2, and the pressure due to the hydrogen is 2.9. So there is no such thing as a gauge that's going to say pressure due to helium equals this. No, all the gauges are going to read total pressure. But the total pressure, 7.2 atmospheres of it is due to the helium molecules, and 2.9 atmospheres of that total pressure is due to the hydrogen molecules. So these are the partial pressures ideas. Partial pressures. Right? And this one would be the total. Okay. Notice how they write these partial pressures. They have a little subscript down there. Right? Okay, some equations for partial pressure problems. So I'll be giving you these. Okay. For our first one here, Stephen. P capital T equals PA plus PB. What do you think those variables mean? Like, what do you think PT probably is? Well, all the P's probably mean pressure, right? So P with a subscript capital T, Sarah, it probably would be total. Yeah, there's my total pressure. And then how about the PA or the PB, Giselle? But not really initial and final, though. Yeah, well, you're close. And one gas and the other gas, right? So they're just saying A's and B's. So it could have been it could have been helium and hydrogen or whatever, right? So those are the what pressures they're called? Partial pressures. If you had 3 gases, well, then you'd just have a PC in there too, plus PC. How about the next one, Mia? What's that one saying? What was the little symbol N for? We saw it once before. It was in this expression. It's the same little N. It's the moles, right? So, Lauren, if N is moles, NT equals NA plus NB probably means what? Yeah, the total number of moles and then the moles of each gas. Just add them up. Okay, this one's kind of an odd one, and I don't think you're going to use it too much, but Rebecca, lucky you. NA and NT. The N's probably stand for what again? Moles. Okay. So if you take the moles of gas A, Megan, divide it by the total number of moles, you get this thing. They call it the blank fraction. Probably the dividing moles of gas A by the total, you probably get the, someone said it, mole fraction. Right? Get the mole fraction. Okay. So that's probably in the homework, but like I said, you probably won't see it too much. But if you add up all the mole fractions, if you have 2 gases, you add up both their mole fractions, well, you better get 1, because if it's, right, half A and half B, you always add up fractions, you always get 1. Okay. Some additional equations, but I'm not giving you these on the exam. Okay. This PV equals nRT, but you add subscripts for A and T. So what does this mean? If we take PV equals nRT, add a subscript, let's start with A, I guess. A, put A's on everything. Now, A is supposed to mean, Paul, what did A mean up here? Yeah, partial pressure. It was PA, right? It just meant gas A, one of the gases, right? So PA would be the partial pressure of A. That's the same PA as what's up there, okay? So it's another way to calculate partial pressure, except, Steph, it really doesn't make sense to put little gas A subscript on some of these variables, because it's the same for every gas in the container. The constant, there's one. Get rid of it there. That does not make sense. Do you see anywhere else, Lorena, where it does not make sense to put a subscript A? Because they all the gases in this container, it's the same for all of them. Do you see another one? Temperature. Yes, they all have the exact same temperature. One gas molecule is going to have a different temperature than the other one. Okay. Temperature is an average over them all. Sydney, is there another one, or are we done? We're done? We done? Everybody agree? There's one more where it's the same for every gas in that container. Volume. They're all in the same container. Okay. So this is just another way to calculate partial pressure, right? We can use this equation up here, or we can use this one. Okay. Let's try it one more time. So you could do that for any gas. Gas A, gas B, gas C. Just put subscripts on the P and the N. You can get partial pressure. T's. T's probably stand for what again, Manuel? Capital T? Well, yeah, usually, but in this case, for subscripts, it stands for total. Yeah, for subscripts. Okay, so we should only have total for a subscript, Emily, on which variables again? P and N, so let's get rid of them here, here, and here. So here's another way to calculate total pressure. If they give you a whole bunch of gases, well, just find their total number of moles, right? And you get total pressure. Okay, so you could use this expression to get it, right? You could always use this one too to get P total, but then you'd have to know the partial pressures, and that sounds kind of complicated. Okay. Collecting a gas over water. This is what you're going to miss out on this week, so we have to save it for next week. It's so sad. We're going to collect a gas over water using this apparatus. You're going to put some solid in here that reacts with heat, and it produces a gas. So you sit here and you waft it and you heat it up, right? And the gas bubbles up, right? No, it doesn't really bubble. There's just a solid there. It just generates a gas, right? The gas goes through the tube, and then you fill this container with water. And there's a hole on the bottom. Well, you have to. There's a tube. So there's a hole in the bottom. It comes up and it bubbles into here. So this will be filled with water, right? And then as the gas bubbles up, it will displace the water. So you're collecting a gas over water. And this is the gas you're supposed to be collecting. Okay? So what's the complication? Well, I'd say I guess we could just jump into the complication right now. If you have water, in other words, we're trying to collect whatever gas we're generating. Like here we're trying to generate oxygen gas. All right? So oxygen gas should be bubbling up in here and displacing the water. So we only want oxygen gas in there. But is that the only gas there? There's also what? What other gas is there? If you have a beaker of water here and you just leave, doesn't the water going to evaporate on you? Right? You can't stop it. So water wants to go into the vapor phase, and if it's sealed, if you put a beaker of water here and you don't seal the container, it's all going to evaporate. Put a beaker of water here, put a cap on it. Yeah, some of the water is going to evaporate until it reaches equilibrium and condenses, right? It's that equilibrium going on. It's evaporating and it's condensing. And once those two rates are the same, the little level won't change anymore. Okay, so it has to be sealed to do that. But the point is that you can't stop a liquid from going into its vapor phase. So not only do you collect the gas you want, you're always collecting water too. So whenever you collect over water, you always get too much gas. Or you always get H2O gas too, however you want to think of it. You always get too much gas. You always get water gas too. Or you can kind of, whatever sticks in your brain. The pressure is always too high. Because you want the pressure to do just to the gas that you're interested in, oxygen. Well, if you collect oxygen and water, well, then the pressure's too high because you got water in there too. You want just oxygen. Okay, so whatever way sticks in your head, right? You're collecting over water. Ah, dang, I'm be collecting too much gas. I'm collecting water too, gas. The pressure's going to be too high. Okay, so let's take a look at this question. This is a collecting gas over water question. So if 35 mils of oxygen gas is collected, so that means you heated this guy up, right? It displaced it, and somehow you had to measure this. We'll do that in lab. There's actually 35 mils of oxygen collected over water at 30 degrees Celsius and 756 millimeters of mercury. How many grams of KClO3 reacted? And this is probably more info than you need to know, but in order for this to make sense, you pretty much have to make these levels the same, and we'll do that in lab. That way you know the pressure inside there. That's the only way to do it. So the pressure will be atmospheric pressure. That's how they measured that pressure. Don't worry about it. Just realize that the pressure inside here, right, is 756 millimeters. Right? The temperature's 30. The volume's 35. Okay? And they want to know how many grams of this KClO3 reacted. Right? How the heck you can get that? That's your answer. Grams of potassium chlorate reacted. Okay. I see 3 steps in solving this problem. There's 3 separate steps. Okay. First, what we're going to do, let's make it a different color here. First, what we're going to do is we're going to find the right pressure. Right? In other words, find PO2. Because the pressure's too high. We got to subtract out the pressure due to water. So we'll do that first. And then, right? And then we'll find the number of moles of oxygen. And if you know the number of moles of oxygen, we can use, what is it called? The what bridge? Mole bridge. And then we can get moles of potassium chlorate, molar mass, and we can get grams of potassium chlorate. So that's the 3 steps. Step 3, use the mole bridge to get, in the end, grams of our answer, KClO3. Okay, so that's the big picture. But how do you do each one of these individual steps? Okay, how do you do each one of these individual steps? The first step, right? Do you see that? Total pressure in this problem is equal to what pressure plus what pressure? P with little subscript what and P with little subscript what? Mia, what would it be? What 2 gases are actually being collected? What 2 gases are being collected in this problem? We're collecting it over water. So we want this one. So definitely that's one of the gases being collected. Anybody, what's the other gas? H2O. Okay. In this problem, that's 756 millimeters of mercury. Which P is that? Yeah, 3 choices here. Which P is it? It's total. You always know the total. That one's 756 millimeters of mercury. We want PO2. So that means this you get from the table, right? Vapor pressure of water at various temperatures. So what you do is you find the temperature we're interested in, which is what? 30 degrees. So using that table, Kenneth, what's the pressure due to water? 31.8. 31.8. And what are the units, though? 31.8, Dylan, he's right. But what are the units? Yeah, it's at millimeters of mercury. Isn't that nice? Because now we have to do any converting. Okay, so we can find the pressure due to oxygen. So the pressure due to oxygen is going to be 756 minus 31.8, which is... And you guys have all my calculators, Mia. Oh, Rebecca, whoever. What's 756 minus 31.8? What is it? 724.2. Thanks, Bobby. 724.2 millimeters of mercury. Okay. So there's our pressure due to oxygen. So that was step 1. Because the pressure they give you is always too high. You got to look in the table, subtract out the pressure due to water. Done. We got the right pressure. Well, how does it help you? It's going to help us by finding the number of moles of oxygen so we can use the mole bridge. Well, how do you find the number of moles of oxygen? What equation would we use? Connor to do this. This is step 2 now.
NT plus
Okay. This one's it'd be too hard, I think, because this one won't quite work because we don't know what the total moles is, right? So it would be nice because total number of moles would be the number of moles of oxygen, the number of moles of water, but we don't know either one of those. So this one won't work. What else could we use? PV equals nRT, there it is. And where do we put those subscripts, Audrey, of O2? Where do we put those subscripts of O2 to make sense out of this? On the P and the N. PO2, NO2. So in that equation, Alyssa, what variable are we after again? What variable are we after? We're trying to do step 2. We're after little n. Don't we know all these? We know PO2. We know V. We know R. No T. Okay. Except R is in what units, Stephen? That big R. Is that big R in millimeters of mercury so we don't have to do any converting? What units of pressure did that big R have? Do you remember? Giselle, you remember?
ATM?
It was ATMs. So we're going to have to do some converting before we plug and chug in this. Right? So let's get pressure in the right units. Right? And then let's make sure everything's in the right units. Okay? And then we'll solve for the number of moles of oxygen. So we'll have pressure due to oxygen, we said was 724.2 millimeters of mercury. Number of moles of oxygen, that's what we're trying to find. Volume, R, and T. Okay, so let's get that pressure due to oxygen. Sarah, let's write down R first, right? R was what again? 0. Yeah, what were the units though? Liters, atmospheres, and I gave you that somewhere. It's on some cheat sheet, right? Over moles times kelvins. It's kind of, I like to write it first because then it reminds me what all the units have to be in. So, Giselle, I have to get those millimeters of mercury into ATMs. Do you remember how to do that?
The bridge.
What was the ratio?
1 ATM is equal to 760.
There it is. She's done it enough that she's got it memorized. Okay, so divide that by 760 and we'll have ATMs. Our volume, someone can give that to me. We can move on. Did you get an answer, Emily? 0.9 what? 5. 0.9. Emily got 0.95. Okay. And we need the volume, but it has to be in liters. Mia, we need that volume in liters. What volume do they give us? Yeah, they gave us 35 mils. Yeah, so what was the ratio to get it into what we want? Lauren, you remember that? What's the ratio to get it into the units we want? There's 1,000 milliliters in a liter. Whoop, 1,000 has to go on the bottom though, right? So you pretty much just move it over 3 places, the decimal point. 0.035 liters. The temperature. Rebecca, how about that temperature? What T should we read? Did they give us? Yeah, they gave us 30 degrees Celsius. Wrong units though, so we have to add what to it? Add 273. So 303 Kelvin. Finally, we've got everything we need. Plug it all in. Is it 32? Oh, change it to 30. Sorry. Change it to 30. I thought you said 32. No, that doesn't make sense. Yeah, change it to 30. Because 32 is not in the table. We can't do 32. More advanced classes you will, because you'll interpolate. That's that ugly word. But anyway, let's pretend it's 30. Make it 30. Okay, so I'll have 0.95, 0.035, my N, my 0.0821, and my 303. Get my N. Connor, did you get an N?
1.34 times 10 to the negative 3.
1.34 times 10 to the negative 3. Anybody else get that? Okay. Several did. Okay. These problems, you're seeing, right? These problems are a lot of work. Okay. Kendall, we just finished step 2. We got the number of moles of oxygen. So now we're supposed to do step 3 and use this mole bridge idea and end up in grams of KClO3. So 1.34 times 10 to the negative 3 moles of what? So we can start this. Moles of O2, exactly. See, it's not that straightforward. Moles of what? It's the moles of the gas we're interested in. We want to do all this converting using the mole bridge and molar mass until we end up in grams of potassium chlorate. So if that's what we want to do, Megan, what would be the first step? Yeah, we found moles of oxygen. Remember, Connor told us it was 1.34 times 10 negative 3. Yeah, so down here. Now we're doing step 3. We should identify these. Step 3, step 2. Here's my step 1. Okay. Who was I picking on? I was picking on Megan. Megan, we want to end up in grams of KClO3. What would be your first step? Use the mole bridge. Perfect. So what would the mole bridge be?
2 KClO3 over 3
Perfect.
moles.
Hear what she said? 2 potassium chlorates for every 3 moles of oxygen. And those 3 moles of oxygen have to go on the bottom, otherwise it's not going to cancel. Okay. We'll let Ashley give us the next one. What's the next one?
1 of KClO3 over the mole of KClO3.
Yeah, grams of KClO3, potassium chlorate, over a mole of KClO3. So we need to add up a potassium, a chlorine, and 3 oxygens. And you get, I hear 122.5. Anybody else get that? Emily, you got that? Megan got it? Okay. Everything on top multiply, bottom divide, and we'll have our answer. Paul, did you get an answer? Not yet. Megan, what'd you get?
0.109.
0.109. Anybody else get 0.109? Yeah. Okay, so we're like 0.11 or somewhere around 0.109. Okay. So whenever you're collecting a gas over water, realize you're collecting too much gas. You're collecting water too. And they're always going to tell you those things. They're always going to tell you the volume of the gas they collected. They're always going to tell you the temperature. So you can look up the water pressure, right? They have to tell you that temperature. And it's going to be a nice number. It's not going to be a 32, right? and then they're going to tell you the pressure that they measured. That's too high. So the first step, subtract from that total pressure the pressure that you find in the table for water. Then use the ideal gas law to find the moles of the gas you collected, because now you have the right pressure. Last step, use the mole bridge to get it into what you're interested in.
So the last step, the 0.09 was our final answer?
0.109 grams of KClO3, because that's what they wanted to know. They want to know how many grams of potassium chlorate reacted. So they're always going to pick something in this reaction and say how many grams of this reacted or how many grams of this was produced.
There's never a shorter way of doing this. You have to do all of it.
This is the only way I see. There's probably another way to skin the cat, Lauren, but I see 3 logical steps. Okay. So there will be those types of problems, but we don't want to blow over the easy ones. So let's just stay where we're at, Steph. And let's see if we can answer some of these. Now we've got, to complicate your life, Steph, I'm going to write down all these equations we've got. We've got PT equals PA plus PB. We've got PV equals nRT. We've got PM equals dirt. We had NT equals NA plus NB. XA equals NA over NT. I think that's about all of them, right? Okay, so I tried to make your life, Steph, as complicated as I could. Calculate the total pressure of a mixture of 0.02 moles of helium, 0.01 moles of hydrogen, in a 5-liter flask at 10 degrees Celsius. So, Steph, you got an idea how to do this? What would be a game plan? Well, we could do that, right? Find the partial pressures for both the gases, and then do what to the partial pressures? Add them up. So she's talking about doing this one, right? And then find the individual partial pressures. That's the hard way. That will work, and you will get the right answer. What's a little bit easier way? What's a little bit easier way? Mm-mm. Yeah, I see it. I see this one. I see this one. I see doing this one first, right? Do that one first to get the total number of moles, then do what? Then what equation? PV equals nRT. But put little what subscripts where? On the P and N. Put what subscript? T for total. Right? So Steph's idea would have worked, but this way is a little bit easier, I think. Right? I would first find NT, right? Then find PT. Right? So NT would be with NT equals NA plus NB. And PT is with PV equals nRT. But you have to put in those subscripts. So try it. Or let's set up. Let's not try it. We know what it is. Let's set up the next one. Don't you think setting up is the hard part, Kendall? Don't you agree?
Oh, yes.
Okay. So you see the game plan. Let's just move on to the next one. Set up the next one. What volume of CO2 at 21 degrees Celsius and 781 millimeters of mercury could be absorbed by 327 grams of copper 2 hydroxide? Oh my gosh, Sydney. So here's all of our equations up here. You have a game plan for this one? Anybody have an idea? one thing that helps me is when I read a question and when they start giving me a volume and a temperature and a pressure, they're giving me all these different things, it almost always points to PV equals nRT. Because that's the only equation that has all this different stuff in it. Everything else, look, PT equals PA plus PB, NT equals, they're all the same thing. The only equation that has all this different stuff in it, look at stuff, volume, temperature, pressure, is PV equals nRT. So to me, that's the hint, is this is the one I'd want to use. And I'm solving for what variable, Emily? Volume. This is what I want to find, is the volume. That means the equation, the problem, had the Kenneth. It had to give me everything else. It had to. So if it did, what would you plug in for pressure?
781 millimeters of high
Yeah.
of mercury.
It's just in the wrong units, but that's the idea. Exactly. You got to plug in the right units, though. Okay, P's done. Dylan, what's another variable that you got? You know.
You convert the grams to moles.
Yeah. Okay. Convert these 327 grams. Convert to moles, because that's what little n is. The question, I think, Bowdy, is moles of what?
Oh, well, that's not what you have up there. Because you changed it of the CuOH, right?
Did I change this question too?
Yeah, over here it's with.
Somehow this thing did not get updated in your book. That's okay. It's the same idea here. You can change it to this one.
But it would be the moles of copper hydroxide, right?
Okay. Now in this equation, this is all referring to pressure of what? Volume of what? Moles of what? Has to be what state? A gas. It has to be the gas. And they kind of gave you a hint, volume of CO2 gas. So this little n has to be moles of CO2 gas. Has to be the gas. It's always the gas. Has to be the pressure of the gas, the volume of the gas, moles of the gas, temperature of the gas. It's always of the gas. So moles of the gas is CO2. So you got to use mole bridge. Exactly. Okay. Well, we know what R is. What would you plug in for T, Connor?
21 degrees Celsius.
Yeah, but you just got to convert it. Exactly. Okay, so there's the game plan for that one. Any question on that? All right. How about a game plan for this one? What are the steps? What are you going to do first? Is this exactly the same? No, it's not. Let's change a little bit. What are the steps? Find the right pressure. That was step one. Then what? Find the number of moles. Right? Using what equation? PV equals nRT. So find the right pressure. Find the number of moles using PV equals nRT. Then, last step, mole bridge. All right? Good deal. Also, have a good break.